Swayam Prabha. Digital India. Educated India.
Welcome to the second lecture of module 5. In this lecture today, we shall discuss the remaining part for the fuse deposition modeling. It will be the die swelling and bead cooling phenomena, the bead deposition, spreading and bonding phenomena, and the surface roughness. And in the end, I shall briefly explain about the other popular polymer or composite based wire processes. So in the previous lecture, we have already discussed about this region, which is primarily for the feeding the wire into the liquefier, consisted of the pinch rollers. We have also seen what should be the value of omega r in order to obtain the desired velocity of the wire. And we have also discussed the two phenomena when wire crushing as well as the slipping between the roller and wire occurs. Also, we have discussed a little bit about the liquefier, and we have also found out the pressure drop which will occur when the wire will enter into the liquefier and convert it from the solid to liquid form and get extruded from a tiny orifice from here. Also, we have discussed in that case what should be the critical height of this wire from the point where it is in contact with the roller to the point where it enters into the liquefier. Now we shall discuss about the third zone, which is what happened when the melt comes out from the nozzle. So mainly now our focus will be on this zone. So the first phenomena which we are going to discuss today is die swelling and bead cooling. In the case of die swelling, what happens? So when the melt is inside the liquefier, it is subjected to the stress, and as soon as this molten material comes out of a tiny nozzle, it usually releases these stresses and got expanded. With the polymer melt no longer constrained by the wall of the liquefier, the stresses those are generated inside this liquefier got relaxed, and the elastically stored energy is released, which leads to the radial expansion. As you are seeing here, the radial expansion of the melt when it comes out of the nozzle, and this phenomena is called as die swelling. The quantitative measurement of die swelling is the ratio of the maximum diameter, which is this diameter of the melt coming out of the nozzle, divided by the diameter of the nozzle at the exit. So if this maximum diameter of the melt is D3, which is divided by then the diameter of the exit diameter of the nozzle D2, this ratio is called as the die swelling ratio. As you can see, obviously D3 is greater than D2 in most of the cases. The value of this ratio S will be greater than 1. It highly depends on the material property and geometry of the extrusion nozzle. Reported value for FDM like processes is around 1.05 to 1.3. However, the inelastic materials such as ceramics usually gives us the reduced phenomena of the die swelling. Instead of having the value of S greater than 1, it may happen that the value of S is less than 1. In that case, it will get contract like this. But that is for inelastic material, those cannot store the elastic energy inside the melt. After leaving the liquefied nozzle in the melt extrusion additive manufacturing process, A bead of polymer melt ultimately lands onto the substrate which is on the bottom. If the flow through the print nozzle region, which is region number 3, which is here, this is region number 3, is modeled as a simple Hagen-Poiseuille flow, the volumetric flow rate Q in this region can be given as Q equals to this formula, pi d2 by 2 to the power 4 delta P divided by 8 eta L2, where d2 is the diameter or the opening diameter of the nozzle at the region 3 and L2 is the length of this region. Now the cross sectional area of the bead deposited on the substrate. So if for example this is the bead deposited on the substrate, so we are interested in finding out the cross sectional area of this bead, and if this cross sectional area is given as AB, area of bead, it will be equals to the AB, the area of bead, into the travel velocity. For example, this entire nozzle is moving with a velocity and that is the traverse velocity Vt. So Vt, AB into Vt, and this will be equals to the flow rate Q, and this flow rate is Q. Now if this flow rate is Q, we can easily find out from here AB equals to Q divided by Vt, and that is what written here. Now we know the cross section which is going to deposit of the bead on the substrate. Now if the print head velocity is sufficiently large, the bead will become unstable and discontinuous. Meaning to say, if your print head is moving with a very fast velocity or very high velocity, in that case you may not be able to get the continuous bead, it may be discontinuous. This is because the bridge transformation may not occur between the die and the substrate. As the speed increases, the bead area is reducing. We can see that from our formula. The formula says AB equals to Q by Vt, and it is obvious now if I increase this velocity Vt, of course my AB will reduce if the flow rate is constant. Of course, if I increase this velocity with a very high value, this area will become very less as well, and hence the bead will become discontinuous. So above a certain speed, the bead will tear and produce gap in the final part. So like you are seeing here the continuous deposition, instead of this, it will look something like this. Then after that it will deposit some material, so it will not be continuous. So the beads are tearing off in between. So the maximum achievable area at the maximum head speed Vt is a similar geometry to a problem of an axisymmetric liquid bridge which is stable up to a height limit on the order of the square of the tip height above the surface by pi. So if the distance between the die opening and the substrate is high, which I usually call as standoff distance, if this height is h, then the possible area, the minimum possible area of the bead can be given as h square by pi. What happened if, for example, you are moving with a speed equals to 1, this is equals to the critical value, 1 I am writing if it is the critical value. In that case, the area will be A1, and what you are seeing here, it is a cross section, right? It's a cross section. If you observe this particular diagram first, you can see we are moving in this direction. So if I want to see in another direction, means if I look from this direction, the viewer is here, in that case the phenomena or the cross section will look something like this. So this is the deposition head which is depositing the bead, and this is the area of the bead deposited. Now if the head speed is 1, in that case the area of the bead will be exactly same under the head which is shown here. So the height is h, of course, and this area and this width is equals to the diameter of the nozzle, that means this is d2. But if you are going slow, for example, you are going slower than this one speed, for example, and that speed is 0.5. In that case, more material will flow, and of course, in that case, your area will bulge out like this. It is happening because your value of Q is constant. So, you can see that from your formula as well. If this is Q, and you can observe it from the formula also, the area 1 will be equals to Q divided by the velocity. So, I am writing it as velocity 1. So, if this value is 1, of course, you will have A1 area. So, if my velocity is reducing to half, then what will happen? Now, the new area A2 will be equals to Q divided by V1 by 2. And hence, your area A2 will be equals to 2 of A1, right? So, as this gap is constant, you are not changing the gap. So, what will happen? The bead will bulge out like this. Now, assume that if your velocity is increasing to twice, in that case, your area 3 will be equals to Q divided by twice of V1. And in other words, I can write it like this. A3 will be equals to 1 by 2 of A1. So, the area will reduce. As our height is constant, this standard distance h is constant, the area will reduce like this. So, the minimum value of this area A, which is deposited on the substrate, the minimum value of this area can be given by h square by pi. If it is less than that, there may be a discontinuity in the deposited bead. Then the continuous bead transfer may not occur and bridge may not occur, and the bead may got tear off, like I have already explained. Now, if I know the minimum area which I can achieve during the printing, then by utilizing my equation for the flow rate, I can obtain the limited value or the minimum value of the traverse velocity, beyond which the continuous bead may not be obtained. So, for that, let us use the formula which utilizes the flow rate, and it says that the Q, which is equals to Vt into the deposited bead area AB, and the value of Q we have obtained by the Huygens equation, which says it will be pi d2 by 2 to the power 4 delta P divided by 8 eta L2, where d2 is the nozzle opening diameter and L2 is the length of this region 2. Therefore, I can easily find out from here the value of AB. So, now the area which we are obtaining from this is written here, and the area which is giving the minimum value of it is written here h square by pi. Now, my velocity which I am trying to find out, if the velocity will increase, this area will reduce. So, its minimum value, the minimum possible value of this area can be h square by pi. If it is less than that, then the bead may tear off. Hence, I can say this value should be greater than h square by pi. Hence, I can find out from here the value of the Vt, and the critical value of the velocity says it should be less than pi square d2 by 2 to the power 4 delta P divided by 8 eta L2 h square. So, this is the limited value or the limiting value of Vt. Beyond this speed, we cannot move our head. As you can notice that the property of the liquid are not directly involved in the stability limit presented in this equation. Therefore, the impact of exceeding the stability limit and the ability of material to neck down from AB to the AB minimum varies based on the Weber number and the Reynolds number of the liquid. Now, let us discuss about the spreading of the bead. When we deposit the bead on the substrate by this process, usually its cross section is of elliptical shape or sometimes called as of oblong shape. So, this shape is shown here. Finally, of course, this shape depends on the viscosity of the melt and the relative surface energy of the bead and the surface on which it is printing. Also, the interaction between the tip of the nozzle, which is depositing the material, this tip of the nozzle and the bead also very much influence the shape of the print bead. As it spreads, the bead is also cooling and the viscosity also keeps on increasing until a solid state is reached. The final width of the rod determines the resolution that can be achieved in the print process as well as the contact area between the neighboring bead. So, the rounded oblong shape of the bead inevitably leads to a small void in the part, and the strength of the bond between the neighboring rod and ultimately the overall mechanical property of the part will depend on the contact area between those beads and the size of the void. So, if this is, for example, is the first bead we are depositing and this is the second bead, the contact area between this and this, which is this much, will very much affect that how much you are going to get the strength. If this contact area is less, I mean instead of getting like this, for example, you are depositing the bead which is having this type of neck, then finally you will end up with having the voids also. So, it is important that how much they are having contact in the end. That will finally define what is the strength you are going to get when you will do the tensile test, for example, on this part in this direction. There is a very important phenomena called as bead ironing. The bead ironing is nothing but the nozzle is usually touches the bead which it is depositing on the substrate. It is very much similar to the die swelling phenomena. When the bead is deposited onto the substrate, it releases the stress, and of course when it releases the stress, its shape will change. To avoid that, we push that bead immediately when it comes out of the nozzle as well in such a way that your top surface doesn't get affected much or its shape remains constant, meaning to say the height, the distance between the top surface of the deposited bead and the bottom surface remains constant throughout. To make sure that, we do the phenomena like this. This is called as bead ironing. So, when the print head nozzle is in contact with the deposited bead, it was found that it is beneficial and resulting in more stable flow and ensuring a flat surface. This is the flat surface which we are obtaining. The distortion of the bead, if you see, this is the distortion of the bead. So, the distortion of the rod of the print head was above the rod surface can be speculated to be due to an effect similar to that is seen in the die swelling. Means if the stresses, when the bead is deposited, there will be some stresses inside and those stresses got released radially in this direction and hence the shape of the bead got distorted. To avoid that, we have seen this bead ironing works very well. And that is why when you see most of these FDM based processes, the nozzle touches the bead and deposited. That is the reason behind that. Now, let us try to understand the bonding phenomena in the deposited beads. The strength of the melt extruded additive manufacturing part will be limited fundamentally by the strength of the bond between the neighboring beads of the material in the part. So, this is for example deposited bead 1 and this is the bead number 2. This bond strength which is happening here due to this contact will be a function of the energy of the adhesion / cohesion, which will depend in part on the contact area between the beads. If the contact area is more, of course this bond will be more. So, for polymer materials, bead bonding occur through a sintering process which emerges through a viscous flow mechanism. So, what happened, for example, this is the bead deposited. Initially, this is the bead cross section you are depositing for the second bead. So, initially they will be in contact like you are seeing here, there will be only a surface contact and this surface contact is for example of a radius A and the diameter 2A. Then after some time the neck formation starts, this is the neck formation and the neck radius or the diameter of this neck, length of this neck I am writing as 2y. After this the diffusion process starts and the interdiffusion of the polymer chain and necking growth looks something like this. In that case, the polymer will form the chain inside the neighboring bead as well. And during this process, this neck radius or the neck width will further increase. Finally, the randomization of the polymer chain between the adjacent rod occur as you are seeing here, and as a result the neck length further increases. The neck length too wide provides a measure of the bond quality. More the value of this neck length, of course better will be the strength of the part. Definitely it will be not possible to get y equals to a, means the deposited surface a, the radius of the rounded corner of the deposited bead equals to the radius or the half of the neck length. That will be almost not possible to obtain. There will be always a waviness, that is why on the top of the surface deposited by the process. However, it is desirable to avoid that, and the necking should form in such a way that you get almost flat surface. Then in that way, if you are able to obtain, the strength of the part will be also very good. This process of sintering is highly driven by the temperature of the bead. The temperature history of the rod at the interface with another rod will be very crucial variable in determining the quality of the bond. Hence, now at this point of time, it is very much essential to understand that what will be the temperature of the bead after, for example, time t when I deposit the material on a substrate. Because due to the ambient condition, it may happen that your heat transfer rate is very high, and immediately when you deposit the material, the bead becomes at the room temperature or the temperature, ambient temperature, very fast, and in that case your neck formation or this process of sintering may not happen appropriately. So if you have seen any FDM process or the machine for FDM, in that the chamber in which we are used to deposit the material is remained hot. In that case, we can eliminate the immediate cooling of the bead and hence allow the part to form this neck or to grow its neck between the two neighbor beads, so that you can ultimately get a very good strength of the part. So now let us try to understand the temperature of the deposited bead at a distance from the nozzle after time t. So first of all, for that, let us assume that the cross section shape of the deposited filament is an ellipse, and as the cross section is ellipse, it looks something like this. Its major radius is shown here as small a and the minor radius is shown as small b. Now the perimeter of this cross section can be given as p equals to pi a plus b bracket 64 minus 3 lambda to the power 4 divided by 64 minus 16 lambda square, where lambda is equals to a minus b divided by a plus b, where a is the major axis and b is the minor axis. Of course, the area of the deposited bead will be pi ab. Please note that this value of the perimeter is approximately calculated here, because if you want to calculate it accurately, there will be an infinite series for that. Now let us also assume a uniform temperature distribution throughout the cross section of the bead, means the temperature does not change in the cross section, it is same everywhere, while the temperature is definitely varying when you are depositing the material. So along the deposition length, the temperature is varying only. Therefore, the cooling process of a single filament is thus simplified into a one-dimensional transit heat transfer model. So the heat is only getting transferred in this direction. The head moves at a constant speed v, for example, along the x-axis. So this is your x-axis you are seeing here. We are assuming our coordinate system to be at the tip of the nozzle, as you are seeing here. So this is the tip of the nozzle and I am assuming my origin here. So the origin is, I mean the 0, 0 is here, and this direction is x. If I am looking anywhere on the back side, that is the direction x, positive x. Because the mass of the foundation is much higher, this mass of the foundation is very large. In that case, the interface which is between the deposited bead and the foundation would not appreciably change the temperature of the foundation. Therefore, the conduction heat transfer, as the temperature of this foundation is not changing, because it is very large, we are assuming it is not changing over the period of time, we will assume that the conduction heat transfer with the foundation is nothing but coming from the convection itself, okay, because it is assumed to be very large and its temperature is not changing, hence its temperature is equal to the ambient temperature. Therefore, the heat transfer or the conduction heat transfer into the foundation is assumed to be from convection only. So, the cooling process of a single filament is thus simplified into a one-dimensional transit heat transfer model, and the heat is just transferring in this direction, or the conduction is happening in this direction. Of course, there is a convection due to the ambient environment and also due to the foundation, because this foundation has assumed to be a very large foundation, and this is also transferring the heat, and its temperature of foundation is not changing, hence it is also contributing from the convection heat transfer. So, now I can write down the one dimensional heat transfer equation like this. Here this is rho C A. Rho is nothing but the density of the material deposited, C is the heat capacity, A is the cross sectional area, delta T by T, where T is the temperature and small t is time, will be equals to A, the cross sectional area, del by del x, K del T by del x. So, this is the conduction in the direction of the deposition, that is in x direction, minus H P T minus T infinity, that is the convection heat transfer, where H is the convection heat transfer coefficient, P is the parameter of the cross sectional bead deposited into the temperature of the bead minus the infinity. Temperature infinity means the temperature or the room temperature. So, these are the boundary condition it is subjected to. It says that the T is equals to T naught at x naught, means the deposited at this point which is 0, 0, where x is equals to 0, the temperature of the deposited bead is equals to T naught, and this T naught is nothing but the melt temperature. Also, at x equals to infinity, means very far away from the nozzle, the temperature of the bead is equals to T infinity, and this occurs after very long period of time. Okay, so we are considering this condition for the steady state only. So, the term H which is written here covers the effect of both heat, the convection heat transfer into the environment and also the heat transfer into the foundation, because we are not assuming any change in the temperature of the foundation. Therefore, this foundation is also considered to be contributing through the convection heat transfer. Therefore, this H is not having only the heat transfer into the ambient, also in the heat transfer into the foundation. Now, if this origin 0, 0 is moving with the velocity v in this direction, hence at any point of time the distance travel x will be equals to v into t, the velocity and the time after that which we are observing. And hence, if we consider the time dependent term which is delta t by del t is equals to, can be written as del t by del x into del x by del t. We know that this del x by del t is nothing but the velocity v. From here itself we can see del x by del t will be equals to v, hence v is written here. Now, this entire equation is a function of x, and hence now I can replace this term del t by del t equals to del t by del x into velocity. Therefore, this equation looks like this. It says rho C A V del t by del x equals to A del by del x K del t by del x minus H P T minus T infinity. This one dimension heat transfer equation is now very easy to solve, and we can solve it, and finally the analytical solution looks like this. So, this is the analytical solution of that equation. It says the temperature T will be equals to T infinity plus T naught minus T infinity exponential minus mx, where m this particular constant is equals to root over 1 plus 4 alpha beta minus 1 divided by 2 alpha, and also x is equals to v velocity and at any point of time which we are trying to observe into t. Of course, alpha is equals to k by rho cv and beta is equals to hp by rho cav. So now from this equation, if you use this equation, you can find out the temperature at any location. Of course, the temperature will be very high at this location, and as you go away, the temperature will keeps on reducing, and the temperature will be at room temperature at infinity. So of course, this equation was obtained by applying those two boundary conditions. Says that at s equals to 0, temperature is equals to T naught, and at x equals to infinity, the temperature is T infinity, that is the room temperature. Now by utilizing this equation, if you have the value of the temperature at any location of the deposited bead, you can easily study the phenomena of the bond formation or the phenomena of necking occur at that location. If this temperature is changing with a very rapid state, means if the H is the value of H, which is considering the convection heat transfer in the ambient and in the foundation, both is very high, in that case the temperature immediately after coming out of the nozzle, after some distance only, will become to the room temperature, and hence this bonding formation may not occur very nicely. If this heat transfer coefficient is low, then of course for a longer period of time the deposited will remain at a particular high temperature, which will help us in forming the or allowing the bead to form the bond with the neighbor beads, and therefore the overall strength of the part will increase. Now let us try to understand what happened when the nozzle starts, stop and takes a turn. The cross sectional area A of the bead can be easily obtained by using this formula, which says AB equals to Q. Q is the volume flow rate divided by the velocity of the head. We have already seen this. As a result, your formula will be like this. It is pi d2 by 2 to the power 4 delta P divided by 8 eta L2 Vt. Now we can observe a few things here. d2 is constant because your diameter of the nozzle is not changing. The pressure difference is also constant if your wire feed rate is constant, and your temperature of the, as your wire feed rate is constant, and as a result the temperature inside the liquefier is isothermal, then in that case your delta P will not change. Also the length of the region 2 is constant, eta is the material property, it will not change, and hence you can see AB is just inversely proportional to the traverse speed. Hence if I increase the velocity of the traverse, of course this area will decrease, and if I decrease the velocity of the traverse, of course this area will increase, and we have already seen that. Now what happens? The velocity is not constant in the beginning and end of the process. In other words, the velocity varies at the start and stop of each successive layer, as well as the same thing occur when there is a sharp turn in the tool path. So if there is a sharp turn, for example you are moving like this and then you are suddenly taking a turn, at this time, for example when you are depositing material in this direction, only X motor is working, and then suddenly you are taking a turn perpendicular to this motion. For example, now you are moving in Y direction, and suddenly the X motor has to stop and Y motor has to start. Due to the involvement of the inertia, now this doesn't happen instantaneously. There is a delay for that. Therefore, the velocity doesn't even change rapidly. It takes some time and form a trapezoidal form. So, due to the change in the velocity or the traverse velocity of the head, what will happen? If it is reducing, the deposited area will be more of the bead. Now let us try to understand how it can be accommodated. And this is the typically shape of the deposited bead. This zone, the first zone from here to here, is corresponding to the starting zone where the print head is just started. Then after that, it will get accelerate and obtain some velocity in the zone. For example, let me write it, this is zone 1. In the zone 2, the head will accelerate and take the desired velocity. Then after that, the region 3, which says that the velocity is constant. Now it is not changing. Then after that, you are going to stop it. It is going to decelerate in this zone. So it will slowly come down to the 0 velocity and finally it will stop. So in that case, let us consider each zone. So let me come back to the first zone, where my velocity is shown here in this red color curve. So the velocity, the traverse velocity is 0. It is not started yet. It is just starting and the head doesn't start moving right now. So velocity is 0, but we will start feeding the wire into the nozzle. As the wire has started feeding, it will also take some time to start the material coming out from the nozzle. As a result, there is no velocity, but you are depositing some material through the nozzle, some finite value, because it will take some time to reach the desired wire feed rate. Some material will get deposited in the beginning like a dot, and that is what you will see when you immediately start your FDM process. Some material get deposited. Then after that, under the acceleration, when the process is start moving, it will change its velocity from 0 to the desired velocity. So Vt is changing linearly now, right? This is following this curve. So the head is accelerating, Vt is increasing, right? If Vt is increasing, head is accelerating, and your deposition head is giving now constant feed rate from the nozzle. As now velocity is increasing, first a necking will occur, means less cross section of the bead will be there, and then finally it will get increased to the stable condition. So slowly the velocity will increase and it will take the final shape. But as there is a finite velocity in the beginning, suddenly a necking will occur. Then after that, the velocity of the traverse and the velocity of the feed, the velocity of the wire into the melt pool, both are constant, and you will get the steady printing, and the shape of the bead will not change much. It will remain constant, the cross section everywhere. Now the similar issues will occur during the deceleration. So what is happening during the deceleration? The head will start coming down from this velocity Vt to 0, and hence the Vt is now reducing. And it is reducing, the head is basically decelerating. In that case, of course, your cross sectional area of the bead now will keep on increasing, because your velocity is decreasing and the material is coming out with the same rate, right? In that case, of course, the deposited bead cross section will keep on increasing like this. And finally, you stops, and now during the stop, some material, as the wire is fed with velocity V, it will also take some time to reach to the 0 velocity. Although now the head is not moving, but due to this finite value of changing the velocity of the wire also, some material will get deposited in the end, that is excess material, like it was deposited in the beginning. So more sophisticated systems available in the market usually have the provision of adjusting the flow rate while depositing the material. So if in the beginning, for example, when the process is starting, less material will get deposited, and in the end, when it is about to stop, the wire feed will also, or the flow rate will also keeps on reducing appropriately. So based on the velocity of the traverse head, if the traverse head velocity is going to be less, they reduce the flow rate as well, so that your bead cross section deposited on the bed will remain constant. So in other words, mathematically, AB is equals to Q by Vt. To keep this AB constant, if there is any change in Vt, they make the appropriate change in the Q. If Vt is increasing, of course, to keep this whole value constant, Q will also increase. If Vt is decreasing, to keep this whole value constant, Q will also decrease. However, we also know that what happened when we try to change the wire feed velocity into the liquefier. The sudden change into the velocity of the wire into the liquefier will disturb the isothermal condition inside the liquefier and the temperature may not be uniform inside the liquefier. In that case, you have to give additional heat quickly from the head also to make the temperature constant inside the liquefier. Otherwise, the pressure drop will increase and there are chances that your wire get bended when it is going to enter into the liquefier. Therefore, the system is not only controlling the flow rate, it is also used to control the temperature given to the liquefier when there is any change into the wire feed rate. However, the start and end process disturbance can be easily eliminated by a very innovative idea also. You might have seen in your 3D printer, whenever it starts, it used to deposit material at some corner in the beginning, and this is only to achieve the steady state. So it starts at the corner, start depositing and then comes to the desired location and deposit the material. So that excess material is just to make sure that the steady state is achieved and now the deposited bead is coming with a constant flow rate and your head is also moving with a constant speed now. As the flow rate and the velocity of the head are constant, it is obvious now that we will obtain the constant bead cross section as well. Now let us discuss a little bit about the resolution and accuracy in the FDM process. Due to the principle of additive manufacturing, many inaccuracies are inherent in it, such as the resolution of STL file itself. Because your STL file is consisted of triangle, which itself is a approximation of the CAD model, you will get the deposition approximated, right? Because you want to make a circle, but you will never able to get a circle, you will end up with getting some polygon. The other source of inaccuracy are like warpage and shrinkage due to the thermal history of the deposited material in these cases. The warpage usually occur due to the thermal gradient available. For example, you are depositing the material and it is having less temperature in the end and more temperature at another end in the end of the process. Due to this delta T, we know that the simple, if I consider just the linear expansion, sigma will be equals to alpha delta T. So due to this delta T and finite value of this alpha, there will be a stress into the deposited part. And when the stress got relieved or we remove the part from the substrate, then immediately it may get warped. So due to that, these inaccuracies are always there in the additive manufacturing processes. So these inaccuracies are inherently there in additive manufacturing processes. The another inaccuracy comes due to the deposition in the layer by layer fashion, particularly at a slant wall. So a defining feature of part made with extrusion AM process are the edge along the surface that result from individual elliptical bead being deposited adjacently to one another. This stair-stepping effect is illustrated in this diagram. So you see that the end condition or the shape of the bead at the end is of elliptical form and you are also depositing on a slant wall. As you are depositing on a slant wall, of course, there will be a staircase effect. Now that will lead to the undesirable surface roughness of the deposited part. Improving the surface roughness by adjusting the design parameter often come at a cost of significantly increased build time. Because for example, you are building the part with a layer thickness maybe T and you are making a slant wall, for example. The one way of eliminating this error is that now, for example, I want to build this line. The one way is that you use the smaller layer thickness. In that case, of course, your RA will be better. So let me just show you also. So if I am now depositing with another layer thickness, then I will end up deposited like this. Now it can be seen, of course, this was the RA value, these are the undesirable areas. Now these areas are small. And of course, the RA value will improve, but on the cost of increasing the build time, because now you are depositing the very thin layers. So we have to make a compromisation. So to make this compromisation, now let us try to predict what will be this RA value for a particular part which is getting deposited at a slant angle. Of course, there is a possible solution for this, that after producing the part by FDM, or these machines, you just go for a post-processing operation such as the mechanical abrasion, machining or solvent vapor smoothing of the part. In that case, you deposit with the thick layers and later on you can remove the staircase by utilizing a post-processing operation. So, although frequently discussed qualitatively, the surface roughness can quantitatively be defined as either the arithmetic average value or RMS value. The average surface roughness RA is the mean variation in the distance of surface profile to the measurement center line, which is defined like this, where L is nothing but the sample length or the evaluation length. Fx is the distance of the measured point on the surface profile from the measured center line LM. So, for example, if you have a part deposited like this, right, and I have a center line first, and I got this center line maybe somewhere here, and I will tell you how to obtain this center line. Then the deviation of this function which I am depositing from the center line, like here it is this and at the bottom also it is this. So, this average deviation, I will calculate, for example, this area 1 and this area maybe 2, and I am considering, for example, maybe this sample length. So, for example, this is also a tiny area coming A3. So, in summary, this RA value can be obtained by A1 plus A2 plus A3 divided by the sample length, that is nothing but L. I am considering from here to here. Also, the RMS surface roughness RQ better accounts for the isolated surface defects, can be defined as RQ equals to root over 1 by L integration 0 to L function fx to the power 2 dx. Now, let us try to obtain the RA value quantitatively for a particular CAD model, for a particular feature which is slanted at an angle theta. So, based on the geometric constraints, a fundamental modeling of average surface roughness RA defined in equation 1 can be obtained for FDM. So, the general approach was to determine the area of the shaded region, which I will show in the next slide, when the rods are aligned at some angle theta in the build plane. Okay. So, the model treats the cross section of the rod as ellipse, as we discussed earlier, in nth layer with the bead width W, assuming that the bead height is H. So, this is how a typical bead looks like. The bead height is H, which is shown here from here to here, and the width of the bead is W. Now, if I am depositing next layer over it, some region will be overlapped, right, and this is the overlap region. Assuming that the height of this overlap is given by C, as you can see here also. Then of course, the layer thickness, or in other words, the distance between this center and this center of the ellipse, the first center and the next center deposited, will be nothing but easily calculated as TL, the thickness, layer thickness, equals to the height of the bead, that is HC, minus the C, this common area, right. So, the same can be obtained from here also. So, the distance, which is the layer thickness, which is nothing but the half of this region and half of this region, is represented here as TL, and half of this common area is nothing but C by 2, and this is assuming to be C by 2. And if my height of the entire layer is H, in that case your TL will be equals to nothing but H minus C, as this is written here. Now, if this is the layer thickness, the center of the next deposited bead or the next deposited ellipse will be shifted by K and H, we know that. So, to obtain this value K in x direction, the shift of the center in x direction will be easily obtained by this triangle. This triangle, in this triangle, this length from here to here, which is shown here in the green color, this length is nothing but TL, the thickness of the layer, and to obtain this value of K, we can easily use, if this angle is theta, this is the slant angle, tan theta will be equals to the TL divided by K, or if I want to obtain K, K will be equals to TL by tan theta. And of course, if theta is 90 degree, this value of K will be 0, because in that case you are depositing just a vertical wall, right? In that case, this K will not be there. Now, I can easily find out if I know the equation of this nth ellipse, and this equation is given as xn square divided by w by 2 square, that is this distance from here to here, that is maybe the major axis, and the minor axis is nothing but h by 2. So, xn square divided by w by 2 square plus y square divided by h by 2 square equals to 1. So, this is the equation of the ellipse at nth layer. Now, to obtain the equation of ellipse which we are depositing at n plus 1th layer can be obtained by this equation, and it says the equation of ellipse will be xn minus k whole square divided by w by t whole square plus yn minus t whole square divided by h by 2 square. So, basically this ellipse, the ellipse corresponding to the n plus 1th layer got shifted by k comma t, where the k is the shift along the x axis and t is the shift along the y axis, and of course this will be my new equation of the ellipse. So, at any location now you can obtain the equation of the ellipse. So, you know the equation of this ellipse, you know the equation of this curve, and you know the equation of this curve as well. So, once we got the equation of the curve representing the cross section of the bead deposited at n minus 1th layer, at nth layer, and at n plus 1th layer, we can easily proceed further to find out the RA value. First of all, we will connect each and every center of these deposited beads, and that will be nothing but representing your slant wall along which you are trying to deposit the material, which is at an angle theta. Now, draw another line which is parallel to this but passing through the intersection points. Or in other words, if I connect these intersection points also, that line will also be parallel to the line shown here, which is in brown color. So, that line is shown here in the red color. If I draw perpendicular to these intersection points on this line, which is shown here in green color, and another will be shown in the blue color here at this intersection point, we can easily obtain the sample length. Now, this is going to be my sample length. Of course, below this red color line, there is material everywhere. But above this red color line, you can see there are somewhere material and there are somewhere no material. That means there are peaks and valleys here. Now, we have to first find out a center line or the mean line. So, to obtain that mean line, we will draw a line parallel to this red line itself, but in such a way that the area into the valley and area into the peak will be equal. So, let us draw a line parallel to this red color line, and which is shown here in the black color, and considering that it is giving you this area and it is given by AV1, area of valley 1, and this area, this is very small area here, this area is given by the AV2, that is area corresponding to valley 2, and the area corresponding to this region, and this is the area of the peak. Now, if this black color line is the center line, in that case the area of the valley, that is AV1 plus AV2, will be equals to area of the peak. Therefore, what is shown here again, the green color area plus the blue color area will be equals to the area which is shown here in the yellow color. Wherever this condition will be satisfied, that will be your center line. And it is very easy to do, because if you are writing a MATLAB code, of course you know the equation of the line passing through all the centers. Then you can easily make a line which is parallel to this brown line but passing through the intersection curve, and then
you can easily write an equation of a line which is parallel to this red color line, but dividing these areas into in such a way that it follows this equality, that is area V1 plus area V2 equals to area of the peak. Now obviously, how to find out these areas AV1 and AV2? It is very easy, because this is nothing but the area bounded by few curves, and you know the equation of each and every curve. For example, this green color area, it is the area bounded between the green color line, the black color line, and this elliptical curve of corresponding to the bead cross section deposited on nth layer. Similarly, this yellow color area is the area bounded between this elliptical curve on the top, the elliptical curve corresponding to the nth deposited bead cross section, and this black color line. And this blue color area is corresponding to this blue color line, which is nothing but the perpendicular to the red color line at this intersection point, and the black color line, and the elliptical curve which is corresponding to the bead deposited at nth layer. So just by simple integration you can easily find out these areas. And once we know the value of these areas, we will make sure that this line LT is parallel to, which is parallel to LV, is positioned in such a way that the summation of green area plus blue area is equals to the yellow area. Once we know that, it is very easy for us to obtain the value of the roughness. Then in that case, the RA value can be given as the area AV1 plus area AV2 plus area AVP divided by the sample length. Now let us discuss some different types of the FDM processes. As the material will be same, because we are still discussing about the FDM process which uses polymer wire as the raw material. Material will be flowed continuously only from the nozzle, and the change will be in the machine tool kinematics. Instead of the serial kinematic, let us have a look at some system they use the parallel kinematics. Again, the energy source will remain same, that is the resistance heating, where the wire coming from the top into the liquefier get melted due to the resistance heating, and the molten material pushes out or extruded from a tiny nozzle onto the substrate. The support mechanism generation or the method for support mechanism is again same. The support which we are depositing will be easily dissolvable into the water. So this is a typical parallel kinematic chain based FDM process. So unlike a serial kinematics, in a parallel kinematic chain, the end effector is directly connected to its base by a number of usually like 3 or 6 separate and independent linkages working simultaneously. So as you can see, this is the end effector where the extruder is mounted, and it is connected with some links simultaneously onto the base. And you can also notice that independent motion of each of these links will decide what will be the position of the end effector. What happen in the conventional serial kinematics? All the links are connected with each other, and then the final end effector is also connected with the same. But here, with the end effector itself, multiple links are connected. So such a printing, what you are seeing here, this machine is nothing but a delta printer, which is usually preferred to increase the Z distance or the Z working envelope. So here, with the very small foot area or the footprint area, you can print really a very large component into the machine. The main advantage is only in the Z direction. Otherwise, the rest of the things are same. Like I have mentioned, there is a liquefier which is giving the resistance heating and depositing the material. The another different classification of FDM is when the machine tool kinematics is not either serial or parallel, but it is hybrid. Means it is a combination of serial and parallel kinematics. So such a machine is shown here, which is using a hybrid kinematics. Here, as you see carefully, This is the AND effector, and this AND effector is nothing but your liquefier. The wire is coming from this hose and depositing the material. Now you can see there is a bed which is moving back and forth and hence giving one axis. Assume that this is the x-axis. The y and z axes are obtained from the top side, and they are obtained by a parallel kinematics. Here you can see multiple links are connected with the extruder, and the motion of the different links are affecting the final motion of the end effector. It is typically a Scott-Russell mechanism. We know already that in a Scott-Russell mechanism, we can easily generate the straight line, and that is why we are able to generate the y-axis motion on this head. But when both the ends of the Scott-Russell mechanism moves together at a particular speed, then as a result we will get the z-axis also here. So here z and y-axes are obtained by the parallel kinematics, while the x-axis is obtained by the serial kinematics. So this is an example of hybrid kinematics. This particular FDM process was, I think, developed by Kappa. Rest of the things are conventional, like the wire is coming from the top and getting melted into the liquefier, which is getting heat from the resistance heating and depositing the material on a substrate. If it comes to generate the support, definitely there must be two extruders here. One can deposit the main material, another can deposit the support material, and the support material will be of such a kind that it can be easily dissolved into the water. The another classification is when instead of depositing the material continuously, we deposit drop on demand. Now in that case, usually one can easily argue that the raw material is not really wire, but it can be in the form of wire as well, because our ultimate focus is to see what kind of drop on demand can be obtained. So this is the machine by Arberg. Like other FDM process, in this case also, we start with the CAD model, do the slicing of the same, obtain the outer contours, generate the inside area filling toolpath, and then process it to the machine. The Arberg machine usually work on a technique should be called as drop on demand. Here the raw material is granules, not wire, which should be our focus today, but it can be wire as well. The ultimate thing, which is the new thing happening on the other side, which is close to the liquefier. So here these granules comes and feed through a screw, and at the end of the screw these granule material get melted and then comes into a nozzle. This nozzle has a plunger, and this plunger moves up and down. Whereas the plunger is moving up and down, it is just dropping the material wherever required. Now the difference here is it is not dropping a continuous material. Here instead it is depositing the drops on demand wherever it is required basically. So this kind of process should be come under the classification of not the continuous deposition, where the material is continuously coming. Here wherever required we are dropping a particular drop of material to deposit it. It repeats, the rest of the process remains same. We deposit the outer periphery and then we fill the inside area, and then we repeat the process and build the whole object like this. After completing the part, it can be taken out, and if required, the support can be removed. So this is basically an example of how drop on demand can be used in FDM. Thank you very much.